About a year ago, I built this light lifting rig, and now it's finally getting lights. But I'm trying something different this time. Focusing optics on my LEDs. If it works, I should get a more dense plant and a lot less light spilling into the room. And if it doesn't, well, I'll have a very fancy nightlight. While I haven't yet had them literally bear me any fruit, I'm really happy with how they've turned out. So what do focusing optics actually buy me? Well, ultimately what I'm after is intensity, which I'm defining as optical power per unit area. And my LEDs output a certain amount of optical power for a given input electrical power, with the difference coming out as heat. But these LEDs spread out their optical power over a big old cone, so there's a lot of that unit area to cover. For my LEDs here, they have a viewing angle of around 130 degrees. Directly over the plant, here's how that looks in my fusion model. A large portion of that cone is extending well outside of my grower, and that means energy wasted lighting up stuff I don't want to light up. So for this build, I'm hoping these focusing optics will help put more photons on the plant where they belong. I'm going to be using a combination of these 15 degree and 30 degree optics, with efficiencies for both around 85%. So I need to be able to aim these narrow cones of light well enough to cancel out that 15% hit from the optics. Enter the side project, LightSim. I wanted something that would allow me to virtually place my LEDs in space and estimate the lighting intensity on the plant. And I'm very happy to say it does just that. I say side project, but I kinda knew this distraction was coming. I've built a couple of takes of this idea over the years, and I find it extremely helpful in figuring out my lighting layouts. This time around, it's written in Python and has a GUI that uses the nice GUI library. I definitely don't think it's absolute accurate, but it's great for relative comparisons, layout A versus layout B. For example, here's how that single cone from the fusion model earlier looks in LightSim. This view shows the light intensity on the imported STL surface. In this case, a lovely plant model I found online forever ago. Thank you to whoever shared it. It's my favorite plant model I've come across. In addition to seeing the intensity on the imported STL, it also has this boundary view. This is my glare on the TV meter, everything that misses the plant. If you put a wall directly around the grower, this would be the light that's hitting that wall. Ideally, that whole boundary would have zero intensity on it, which would show here as a nice dark purple. But it's unlikely that nothing will hit it, so I decided my goal is to keep the total power hitting the wall to less than 10% of what's hitting the plant. Looking at the boundary here for our single unaltered LED, all that yellow, that's bad. Targeting less than 10%, well, this one is 250%. Granted, this light is higher than it should be for the height of this plant, but even at a more reasonable height of about 4 inches or 100 millimeters above the plant, it still only comes down to around 50%. Looking at it side by side with one with a 30 degree optic on it at the same power, look at all that lovely lavender. So I needed to try and aim my lights to try to get these spotlights all over the plant. And for the current build, here's the configuration I decided to go with in hopes of getting that. It has a total of 24 LEDs divided into 6 groups of 4. The LEDs are all positioned radially outward and then rotated to point inward toward the plant. Not optimized, but I tried to balance optical performance and mechanical design. That balance still meant I needed to hold my LEDs out at compound angles cantilevered away from the lifter's supports. And in a very out-of-character move, I decided I needed a proverbial $10 solution for my $1 problem. But I sure had fun doing it. I decided I was going to call on the folks over at PCBWay to go with Selective Laser Melt printed aluminum parts for my light mounts. Now hear me out. This not only allows me to position my lights at the compound angles I want them, but also helps manage all the heat these high-power LEDs dump out. The thermal conductivity of SLM printed aluminum is typically a bit less than that of wrought aluminum, but it's orders of magnitude better than plastics like PETG, and the textured surface of metal printed parts usually helps with convective cooling. So while it may sound overkill, I actually think metal printing is a pretty awesome option for these kinds of applications. And if PCBWay hadn't been nice enough to let me have them for free for this video, they only would have cost me just under $145 for all 6 of them. I've said it before and I'll say it again, it blows my mind that us home tinkerers now have access to this kind of stuff. So awesome. But I digress. Back to that discussion of the thermal properties of the mounts. Each one of those LEDs can put out over a watt of thermal power at my max current, and that's why you see all these random features around the parts. I'm not a thermal expert, so I basically treated this like more surface area equal more better. Pins, slots, holes, if it looked like it might help, it went in the model. Since I have access to it in Fusion simulations, I did decide to try my hand at a thermal sim. I trust these results even less than the mechanical FEA I do in Fusion, but it is pretty cool being able to visualize the airflow and to see what temperatures it predicts. Plus, I just like the way it looks. It was after looking at the first result like this, which shows the predicted airflow around the mount, that I decided to add all those cutouts around the perimeter. I saw that the pins I added, sticking out behind the LEDs, are sort of in the wake of the mount, so, more surface, more better. These holes that run along the stem are some of the few that aren't there for thermal. They're there for strain relief points for the wiring, and up at the top of the stem is the interface for attaching to the extrusions. The interface is narrow to allow it to fit between the brackets on the lift assembly, and that allows me freedom to position them wherever I want, radially along the extrusion. In adding all those features, I was thinking, printers don't care how many features you include, but I forgot about one thing that printers do care about. I submitted the files to PCBWay, and they quickly emailed me like, so about these tiny features. I could have submitted revised files, but I chose chaos. I figured if the fins didn't print perfectly, that's just bonus surface. But I didn't get to test my bonus surface theory because they came out great. I didn't put them on a CMM or anything, but I was pleasantly surprised by how all my swagged features turned out great by my eye. My original plan was to tap these holes here for M3 screws that would hold the LEDs in place. Then I realized the optics wanted the exact same real estate, so I upgraded to the permanent fastener, JB Quick. But to at least pretend it was official, I did make some printed jigs to keep the compression and the thermal paste as the JB Quick set. Once I had the mechanics in place, I crimped what seemed like an unlimited number of connectors and wired everything up. But wired them up to what, you might ask? Well, I split my 6 light modules into 2 sets of 3, and each of those sets routes to one of these driver enclosures mounted to the top side of the extrusions. And inside of those enclosures are some custom PCBs that PCBWay again helped me out with. Each channel, which is 3 lights of the same color, is run by a constant current driver that puts out from 0 to 1 amp proportional to the duty cycle of an input PWM signal. And instead of running a bunch of control wiring to supply those PWM signals, each board has an ESP32C3, that's a fun one to say, that pulls set points from a database on my Synology NAS. Not only does this mean I don't need to send signal wires to these drivers, it also means I can easily set system parameters or check measurements from any device on my network, so I get to feel extra nerdy about it. To get the power in, each board has a barrel plug for a 12-volt DC supply coming from the lifter winch, which I showed in my lifter video. I also included a connector here to allow me to make use of the unused GPIO pins to piggyback sensors or whatever else I might want down the line. But I do have a confession to make. My EE ineptitude caused me to miss a trace in my layout, so I had to ruin that lovely matte silk screen with a patch. Luckily, I was able to find the error and get my improvised fix in place relatively quickly, but then I spent nearly 2 days to figure out I forgot to solder 2 pins. So, ups and downs. Yeah. But after all that, it's been working great. Before installing them on the system, I made the brightest little Christmas tree I've ever had. I used this and similar setups for some break-in testing. Just getting some sanity checks on power draw, operating temperatures at different currents, and that kind of stuff. And of course, did a photo shoot with a humidifier, as one does. But with the humidifier off, I also used this orientation to do a little comparison to the thermal sim. The simulation predicted the aluminum would be pretty consistently above 50 degrees Celsius, but I measured with both this little thermal camera that piggybacks on my phone and with an IR gun. The highest temp I saw in the metal were between the pins, where it got into the mid to high 30s. I was running it at about 750 milliamps, which should result in about the 1 watt of heat I modeled. It was pretty cool in the basement when I was doing these tests, around 15 degrees C, but I reran all the sims at the same ambient, so the comparison should still be fair. If you have any thoughts on what I may have wrong in my modeling, I'm all ears. After the testing and glamour shots, I went ahead and mounted everything on the light lifter. I can still freely adjust the light module positions along their extrusions, so before I have a seedling too far along, I'd like to try and optimize these positions a bit using LightSim. But I'm gonna need to hurry, cause I got impatient.